In this lecture, we will be talking about various physical, chemical, or nutritional changes occur in proteins during food processing. These processes can have desirable or undesirable effects on protein quality. Moderate heat treatments. As you learned before, proteins are denatured when exposed to heat. Most food proteins are consumed in their denatured state. Moderate heat treatments between 60 to 90 degrees for 1 hour or less results in partial denaturation. Protein denaturation may be desirable or undesirable depending on the circumstances. Let's see them. Denaturation at moderate heat treatments increases the digestibility of a protein, improves the digestibility, often makes it more palatable. Because digestibility is a problem in several plant proteins and egg protein preparations. So they exhibit poor digestibility. So with moderate heat treatments, their digestibility improved. So this graph shows the change in digestibility following moderate heat treatments. There are different plant proteins here at different ratios. They generally increase after applying heat treatment, especially lentil. There's a 41% increase in digestibility after the treatment. Okay? All samples' digestibility are increased at different ratios. The other advantage of this moderate heat treatment is no toxic derivatives are developed. Okay? So we apply heat, we change the structure, but there is no toxic byproducts, no toxic derivatives. So this is an advantage. So let's see the other effects. Moderate heat treatments are useful to inactivate anti-nutritional factors. So what are these anti-nutritional factors? Many legume and oilseed proteins contain several trypsin inhibitors, an anti-nutritional factor. Okay, I'm going to write here. So these inhibitors impair digestion. Digestion of proteins. So what happens when digestion is inhibited? The availability of proteins will be reduced. They won't be available to be absorbed by the body. The biological availability. Reduced. Okay. Let's see again. We have trypsin inhibitor, found in many legumes and oilseeds. And we also have lectin, another anti-nutritional factor. So lectin is glycoprotein. So it exhibits a high binding affinity for carbohydrates. So when consumed by humans, lectins impair protein digestion and cause some intestinal malabsorption of other nutrients. Milk and egg proteins also contains several inhibitors. Here, plasmin, avomucil. So all these inhibitors lose their activity when subjected to moderate heat treatment, especially in the presence of water. So they are not stable to heat. So these anti-nutritional factors do not pose problems when cooked, okay, when heating conditions are enough to inactivate them. Okay. They are inactivated. Here, as you see in this graph. So this is the toasting temperature for soybean flour, and we see the decrease in trypsin inhibitor as we increase the temperature this way. So it's inactivated as we increase the toasting temperature. Okay, let's continue. So from a nutritional standpoint, partial denaturation caused by moderate heat treatments improves biological availability of essential amino acids. So we have 9 essential amino acids. So what are these? Remember, before we said we have 20. So we have 20 primary amino acids, right? So among these 20 amino acids, 9 of them, okay, essential. They are essential amino acids, essential. So why do we call them essential? We call them essential because they are not synthesized in animals and humans. That means they can't be made by your body. And that's why they must be obtained through your diet. So what are the best sources? So animal proteins are the best sources, like meat, egg, poultry. So when you eat protein, it's broken down into amino acids. So they are the building blocks. These amino acids are used in various processes in the body, such as building muscle, regulating immune function. Okay. Since digestibility is improved with moderate heat treatment, so biological availability of these essential amino acids are improved. As we said in the previous slides, they will be biologically available to be absorbed by the body, because these anti-nutritional factors will be removed, which impairs digestion. So when we improve the digestion, we improve the biological availability. Okay, let's continue. Denaturation at moderate heat treatments also inactivates several enzymes, such as protease, lipase, amylase, lipoxygenase, and other oxidative and hydrolytic enzymes. So what is this important? Okay, why it's important? Failure to inactivate these enzymes can result in development of flavors. Okay. So what else? Rancidity, textural changes. And discoloration of foods during storage. So as an example, oil seeds and legumes are rich in lipoxygenase enzyme. And you wanna maybe extract an oil from an oil seed, or you wanna extract a protein isolate. So during crashing of these beans, this enzyme, especially in the presence of oxygen, catalyzes oxidation of polyunsaturated fatty acids, right? Polyunsaturated fatty acids. And it might yield hydroperoxide. And these hydroperoxides also decompose into secondary oxidation products, and which impart off flavor in the protein isolates or in the extracted oil. Okay, so to avoid that off flavor formation, it's necessary to thermally inactivate these enzymes, okay, prior to process. Okay, let's move on. The beneficial effects of heat treatment also include inactivation of protein toxins, such as botulinum toxin, and Staphylococcus aureus. So for example, this Clostridium botulinum. How can we inactivate? So 5 minutes at 85 degrees Celsius is enough. Inactivates that toxin. But not all toxins are inactivated by heating, because many toxins are non-proteinaceous. That means many toxins do not contain protein, and they are not denatured by heat. For example, Escherichia coli. Heat stable. Okay, not all toxins are inactivated by heating because they do not contain protein. Okay, we saw that moderate heat temperatures have beneficial effects on protein digestion and quality. So let's see what happens when they process at high temperature. So pyrolysis. Proteins undergo several chemical changes when processed at high temperature. So most of these chemical changes are irreversible. Okay. And some of these reactions result in formation of modified amino acid types, which are potentially toxic. Okay. So toxic byproducts are produced at high processing temperatures. So when we talk about pyrolysis, it's a severe heat treatment when proteins are heated above 200 degrees Celsius during the processes such as during broiling, baking, and grilling. So these amino acid residues undergo decomposition and pyrolysis. So these pyrolysis products, especially identified from broiled and grilled meat, are highly mutagenic. Okay. Mutagenic, also we can say, because they carcinogenic. Okay. They are carcinogenic compounds, mutagenic. So the most carcinogenic, mutagenic products are formed from pyrolysis of tryptophan and glutamic acid residues, especially. Tryptophan, I will write the 3-letter abbreviation, tryptophan and glutamic acid amino acid residues. Okay, the most mutagenic products are formed from pyrolysis of these 2 amino acid residues. So in this figure you see the 3 most potent mutagens formed in a broiled fish. That's the most common. They are generally called IQ compounds. Imidazoquinolines, IQ compounds, which are condensation products of certain amino acids. Okay, these are not good for our health. So generally, following heating of foods according to recommended procedures, IQ compounds are maybe present only at very low concentrations. So proper heating is important. Okay, continue. You already learned about Maillard reaction in carbohydrate chapter. So as you know, among the various processing-induced chemical changes in proteins, this non-enzymatic Maillard reaction has the greatest impact, especially on the sensory and nutritional properties. It's a complex set of reactions initiated by reaction between amines and carbonyl compounds at elevated temperature. And it results in browning, flavor alteration, reduction of nutritional value. Again, we have some mutagenic products, okay, and some precipitation. Okay, you already learned about them. That reaction requires reducing sugar and free amino group. Okay, let's move on. Racemization and beta elimination. So thermal processing of proteins at alkaline or acidic pH leads to racemization. It can be a partial racemization or full racemization. So it's, remember amino acids have 2 isomers, L and D. So it's basically conversion of L amino acid residue to D amino acid residue. So that's the racemization reaction. It can happen at acidic or basic pH. But here this figure shows the mechanism at alkaline pH. It involves the initial abstraction of the proton from the alpha carbon by a hydroxyl ion. And the resultant product is called carbanion. So this carbanion loses its tetrahedral asymmetry. And subsequent addition of a proton from solution can occur either from the top or bottom of the carbanion. And this results in racemization of the amino acid residue here. It starts with L and converted to D here. And what factors affect the rate of this reaction? So, okay, let's write here. The rate of racemization of an amino acid residue is affected by the electron withdrawing power of the side chain. Withdrawing power of the side chain. So some amino acids such as, okay, right here. I will write the abbreviations: aspartic acids, serine, cysteine glutamic acid, phenylalanine, and thymine. So these amino acid residues are racemized at a faster rate than other amino acid residues because they have that functional side chains with electron withdrawing power. So the rate of the reaction also dependent on hydroxyl ion concentration. But it's independent of protein concentration. Also, the rate of reaction in free amino acids are greater than proteins. Okay. It's like the rate is about 10 times faster. So 10 times faster in proteins than free amino acids. So it's the other way, sorry. Okay, so what's the meaning of this reaction? What happens with racemization of amino acid residues? So racemization of amino acid residues causes a reduction in protein digestibility. Okay. Because the peptide bonds involving in the amino acids, they are less efficiently hydrolyzed by gastric and pancreatic enzymes in the intestine. So they won't be absorbed well, and this leads to a decrease in nutritional value. Even some D amino acids, as an example, D-proline is neurotoxic. So it's not a good form in terms of digestibility and nutritional value. Okay, that's racemization part. We also have a beta elimination reaction here. So what's that one? So depending on the reaction conditions, this carbonium formed under alkali pH also can undergo beta elimination reaction. Okay, so this part is the beta elimination reaction this way. And it yields a reactive intermediate. It's called dihydroalanine or DHA. It's highly reactive. So it's highly reactive intermediate, so it involves in several protein cross-linking reaction, a set of complex reactions. So what is protein cross-linking? We can just simply say it's the process of binding two or more protein molecules together to facilitate more protein-protein interactions. These cross-linked protein polymers are mechanically strong and resistant to heat and attacked by solvents. So depending on the situation, it can be desirable or undesirable. In some cases, the protein solubility decreased. Protein loses some of the functional properties, like emulsification. Okay, it depends on the endpoint and the end use. Okay, let's move on. Oxidizing agents such as hydrogen peroxide and benzyl peroxide are used as bactericidal agents in milk, as bleaching agents in cereal flours, protein isolates, and fish protein concentrate. So several oxidative compounds are also produced in foods during processing. These include free radicals formed during irradiation of foods, during peroxidation of lipids, or during non-enzymatic browning of foods. And these are highly reactive oxidizing agents. They cause oxidation of several amino acid residues and polymerization of proteins. The amino acid residues most susceptible to oxidation are methionine, cysteine, tryptophan, histidine, and tyrosine. Let's see some examples. So methionine is easily oxidized to methionine sulfoxide by various peroxides. So methionine becomes biologically unavailable once it's oxidized to methionine sulfone. Okay, so it won't be biologically available. Also the homocysteic acid. Okay, when we convert methionine, these two oxidation products, it's not biologically available anymore and our body cannot use it. And here you see oxidation of cysteine and cysteine under alkaline conditions. They follow beta elimination reaction pathway to produce but these oxidation products are still biologically available. Okay, let's continue. Deamidation reaction. It's a chemical modification. Amino acids are chemically modified to change the functional or nutritional properties. So this reaction involves the removal of amide groups. So we have glutamine and asparagine with amino groups here. With the removal of amino groups, they are converted to glutamic acid and aspartic acid. So there is increase in negative charge and increase in hydration with liberation of carboxyl groups. So as a result, there will be improved solubility, water binding capacity, foam expansion, emulsion viscosity as compared to their unmodified counterparts. Okay. So let's see another chemical modification, acylation. So it's the reaction between amino groups and several acid anhydrides. It's a chemical modification. Common acylation agents are acetic anhydride or succinic anhydride. So common acylation agents. So reaction of protein with acetic anhydride results in elimination of the positive charges of lysyl residues and a corresponding increase in electronegativity. So when we increase the electronegativity of proteins, we unfold the protein, and extensive reaction is allowed to occur. Because of this unfolding, that's why acylated proteins are generally more soluble than native proteins. Here you see a graph. So, chemically modified acylated forms better solubility. More soluble compared to native one. And let's see the last one. Phosphorylation. So it's another chemical modification. It's involves the introduction of phosphoryl residues. And resulted in increased negative charge, increased the protein electronegativity. Depending on the protein type, solubility can improve or can be reduced. But from nutritional standpoint, there's an increase in phosphorus content. But there's no significant change in digestibility. Okay? That's all for this lecture. Let me know if you have any questions.